So thank you all for sticking around to the end of the day for me. I really appreciate the invitation from Marnie and the other organizers to speak, and I'm very sorry that I'm not able to be there because there are a number of you that I know from email or Twitter that I would have loved to have had the chance to meet. Unfortunately, my family situation didn't allow that. So my talk will be about how we can tell whether or not light pollution is getting better or worse, and let's get started with the slides. So this is a picture of Calgary, Alberta, two photos taken from the International Space Station by astronauts. And what you can see is that lights worldwide and in individual cities are changing. You see, for example, at the center left of the image, there is a neighborhood that switches from orange to white. And that's replacement of sodium vapor lamps with white LEDs. You can also see towards the bottom right that there is a freeway that is newly illuminated. And this is a freeway that existed but wasn't lit before. And so that's a type of new lamp. LEDs are allowing all kinds of new lighting. If you do a Google search for bridge lighting, you'll see, for example, that a bridge is no longer simply a way to get from one side of a river to another. It's now a light spectacle that takes place every evening, a big light show. When we look at the lights on a really broad scale, like here from Europe, and we study how they're changing, what we see is that lights are globally increasing, and I'll come to that in a moment. And what makes up these lamps is not only our street lights and bridge lights, but also advertising lighting, light escaping from windows, all those different types of lights. And all of that is changing with the conversion to LEDs. Now, there's a problem with when we look with our global satellite view in terms of this transition to LEDs. And I can show that here with these pictures from Milan in Italy. You see that the city center changed from orange to white, from sodium vapor lamps to white LEDs, whereas the countryside surrounding Milan stayed orange. Now, that was with the astronaut photographs. They can't cover the whole world, but they can cover individual cities with color and with high resolution. When we look at the global data set, though, it looks as if Milan got quite a bit darker. And the reason for that is that the satellite doesn't have sensitivity to light below 500 nanometers. So that's blue light. That means the global Earth observing satellite for nighttime systematically undercounts LED lights. Of course, it sees them, it just counts them as being darker than it ought to. Now, despite that fact, when we look globally or at the national scale for how lighting has changed, what we see is that nearly all the countries in the world, including the wealthy countries that are converting to LED, are increasing both in the area that is illuminated. So that's, for example, illuminating that freeway for the first time that we saw in the earlier photo of Calgary. And also when we look at areas that were illuminated in all of the years 2012 through 2016, we see that those areas have become brighter. So there's two things going on. One is we're putting lamps into new places, and the other is that for some reason, even though we undercount the light from LEDs, our cities on average are becoming brighter. Of course, that affects the sky brightness that I think you've probably had a lot of talks on. On the left, you can see a place that I go to do field work about 100 kilometers away from where I am right now. We have a beautiful view of the Milky Way, not as nice as yours in Siding Spring, of course, and I would hope that you don't have that orange glow around the horizon that is caused by light pollution, but still quite nice. You can contrast that with my institute where I work, where you can definitely see stars, but it's nothing at all like that picture with the Milky Way. 2 years ago, my colleagues and I published a worldwide map of our predictions for how bright the sky is at any location. And you can access this data and look at predictions for your home or places where you'd like to go vacation. The problem with this method, though, is that it's based on that satellite data. And that means that going forward, we can't really use that method to predict how bright the sky is. Coming back to the question of sky brightness, I have to explain a little bit about the physics of light in the atmosphere. It probably has already come up at the conference, but just to let you know in case it hasn't come up, The reason that the sky is blue has to do with the scattering of white light in the atmosphere. So if you imagine the sun shining straight downwards at noon in the tropics, the sunlight outside of the atmosphere is white. And as it goes into the atmosphere, some of the light is scattered away from the direct beam of sunlight. And blue light is scattered more than other colors. So you see that that's what produces the blue sky when you look in any direction that's not towards the sun. So the reason for this is related to atmospheric scattering off of small molecules. So red light also scatters. There is a red light component in the sky brightness, but blue light scatters much more. So when we have white light from the sun coming through the horizon, it has to travel through a lot more air. And that means that first a lot of the blue light from the sunlight gets scattered out, then the green, and then the yellow, and you get left with this really red setting sun. And the sky color near the sun will also be different from the middle of the day. The same thing happens if we think about white light from our cities shining up towards the atmosphere. Of course, red light will also be scattered. Sodium vapor lamps also produce sky brightness, but blue light is scattered more. And so when we compare a white LED to an older high pressure sodium lamp, you can see that the LED is going to be producing more sky glow for the same total amount of visible light. That's assuming that the lamps otherwise were exactly the same, which, to be fair, is rarely the case. This blue light has another problem, which is that when we are stargazing, we are not using our daytime vision. So when we look here on these two curves, the top one shows the light that is output from a typical high pressure sodium lamp, and the bottom for a relatively cool color temperature LED. You can also see labeled on these two curves is a line that shows where sort of the peak sensitivity is for our daytime vision, that's photopic, or for our nighttime vision, that's scotopic. And you can see that the white LED is putting out a lot more light in this region where we use our nighttime vision. And so not only do we have more atmospheric scattering, we have more light where it's problematic for stargazing. So the question is then, what is this change to LEDs going to do, right? Because one thing I should mention, I sort of mentioned this, that most LED street lamps that are being installed these days are actually pretty good lamps. This is a photo from my hometown. You can see it actually, as it turns out, it snowed there 2 nights ago. So it might actually look like this right now in September. I'm sure it's much nicer where you are. In any case, they have really very nice distribution of the light there. As a pedestrian or a driver, you don't see the lamps up ahead on the street. You only see the lit street. You can also see that there's a very strong cutoff that the agricultural field on the left side of this photograph has no light shining on it whatsoever. So it's possible to drastically reduce the total amount of light emissions by using better optics, and LEDs allow that quite easily. The other thing that some communities, but not all, will do is that because white light appears brighter for the same amount of visible light compared to orange or red light, some cities choose to decrease the brightness of the lamps. And of whether or not they do that will depend on your community. But the point is, there's a number of reasons why we could imagine that a transition to LED streetlights could help the sky, as well as other reasons why it could make it worse. So to look at one of the very few concrete examples that exists, these are photographs taken by Zoltan Kolath and then converted into numbers that we can understand. So in this picture, that NSU scale stands for natural sky units. So something that's blue is a sky that's about 2 times brighter than a starlit sky, and an area that's green is about 5 times brighter than a starlit sky. So on the left was the situation when the town had sodium vapor lamps that had a relatively large amount of direct uplight. And on the right is after they switched to LEDs, to white LEDs, which controlled the light more carefully. You see that the sky glow was reduced quite a bit in this visible band. That's mainly green light. When you look at red, you see that the decrease was really, really dramatic. And when you look at the blue, you see that, well, actually, there wasn't so much of a decrease. But on the other hand, it didn't get worse. So in this town in particular, it appears that the LEDs helped, but it would be very easy to imagine a situation where you have a reduction in red light and an increase in blue light. And then the question is, did the sky get better or did it get worse? So I was very pleased that the editors of Nature Astronomy invited me to write about this topic. And my opinion is that the only way that we can address the change in sky brightness for human beings is to actually measure it. And so that means that we need to involve amateur astronomers and other citizen scientists in measuring sky brightness with their visual perception. When we do that, we get data like this that I show here. On the vertical axis, you see for the astronomers, that's naked eye limiting magnitude. For everybody else, it's an index of how many stars you can see. So if you're up at 5, you're getting up to say like 1,000 stars. If you're down at 3, you're down to about 100 stars or so. And then on the horizontal scale, you see how bright we predict the sky is in comparison to a starlit sky. So 10 means 10 times brighter than a starlit sky. And you see that when we group the data in this way, there's a really strong connection between the average of how many stars people say they can see and how bright we predicted the sky to be before the LED transition began. So this is the best technique that there is to measure how sky brightness is changing, because it accounts for everything. It's using the human eye, and we'll get the correct answer by doing this. The problem is we need a lot of participants. So just to quickly show a couple of the experiments you can take part in. Globe at Night is the sort of the classic one. It's been around very long and has a very simple use. You just look at a star map. Here you can see Orion, and apologies for Orion being upside down, but my computer at the moment is in the northern hemisphere. That would be what it would maybe look like at Siding Spring, except upside down. This would maybe be in the center of Beijing, maybe in Sydney, I'm not sure because I haven't been there. In the center of Berlin, not far from where I am right now, Orion typically looks something like this. So by selecting which of these star maps matches your sky, then you can tell us about how bright the sky is. The other technique we have is the Loss of the Night app, which is a program that I developed with colleagues here in Germany. And in the Loss of the Night app, we direct you to look for individual stars and tell us whether or not you can see them. So again, in this example, I'm looking for Polaris. You would never be asked that in the Southern Hemisphere. And I have to say whether or not I can see Polaris. If I'm not able to, then I can give feedback about why I can't. So it could be that there's a tree in the way. It could be, you know, it's just hard to tell where anything is because there's not very many stars. Or it could be, I know where Polaris should be and it's definitely not there. Now, when we look at the data that we get from the app, I'll show that here. Again, this stellar magnitude tells you about how many stars you can see or how bright the stars are. So the lower numbers are the brightest stars. And on the horizontal axis, you see the time when people made the observation. So here's the first example of an observer with not particularly self-consistent data. So I'm going to circle the stars they couldn't see, and you can hopefully see the stars that they can see. And you see that the data is not so self-consistent. They said that there are some faint stars they can't see. On the other hand, they said there's some bright stars they can't see. But that's no problem, and don't worry about it if it happens to you, because we can assign a relatively large uncertainty to this observation. As you get more practice and better with the app, you'll be able to make more accurate observations. So we see here that in this case, all of the stars that the observer said were not visible are fainter than all of the stars they said were visible. So we can have a lot of confidence that they made that observation correctly. And finally, for the really truly dedicated people that love observing stars, this person looked at 35 different stars, and you can see that there's a very good separation between the stars that they reported they could not see and the stars that they reported they could see. So we can have a lot of confidence, and this is a much more accurate measurement than is possible with Globe at Night. So the key to tracking how sky glow is changing on global scales is getting data from around the world. And we've been doing fairly good with this when you look at the global scale, but when you look at national scales, in most countries, there's not enough data. And that extends to Australia and New Zealand. You can see here that you have maybe 500 observations in the last decade and a half. Unfortunately, to get a good measure of how the sky is changing, you would want to have more like 500 observations a year. So if you want to be able to see how Australia and New Zealand are changing with the transition to LEDs, you're going to have to ramp up the participation of amateur astronomers and the participation of other citizen scientists. You can get school kids involved. You can get anyone involved in Globe at Night. It's really easy. So with that, I'd like to leave you going back to the idea of the very first slide. And I probably don't have a good sound connection, so I'm not going to sing, but I'd like to say a little poem with apologies to Bob Dylan. Come gather round people wherever you roam and test the sky brightness to see if it's grown. Because you know if you don't, it'll just stay unknown. If the stars to you are worth saving, then you'd best start observing before they are gone, for the lights, they are changing. Thank you very much, and I look forward to any questions that you have.